Welcome to our lesson on section 2.5 on continuity. In this lesson, you'll learn about the definition of continuity, types of discontinuities, types of functions that are continuous on their domains, and the intermediate value theorem. A function is continuous at a number a if the limit of f of x as x approaches a is equal to the function value at a. Informally, a function is continuous if you can draw it without having to pick your pencil up off the paper. A break in the graph is called a discontinuity. In the graph in case number 1, since there are no breaks in the graph is continuous. In case number 2, there's a break in the graph. However, we could make the graph continuous just by changing the value at f of a. This is called a removable discontinuity. A jump discontinuity, as in the third case, approaches different values from either side of a, and an infinite discontinuity has some type of vertical asymptote. Let's use graphs to determine the continuity of some piecewise functions. This graph approaches different values from the left side and right side of 1, so this is a jump discontinuity. Even though this piecewise function is made up of two different function graphs, it is connected at x equals 1. That makes this function continuous. The first piece of this graph has a vertical asymptote at x equals 2. The second piece is just the point 1, 2. This has an infinite discontinuity. Let's look at some theorems about continuity. For functions that have an endpoint with no values on one side, the function is continuous at that endpoint as long as the one-sided limit exists. Y equals the square root of x is a good example of this. The graph is continuous at the endpoint 0, 0 because the limit as x approaches 0 from the right exists. Thus, a function is continuous on an interval if it is continuous at every number on the interval. As a consequence, if these two theorems, it follows that polynomial, rational, root, and trigonometric functions are continuous at every number in their domains. We'll need to use this theorem to prove other things in another unit later in the year. This theorem basically says that if functions f and g are continuous, then so are the functions formed by their sum, difference, product, quotient, constant multiple, and composition. In this course, there's a small number of theorems by which you'll need to refer by name. The intermediate value theorem is one such theorem. When you copy this one in your notes, put a box around it with big stars. Formally, the intermediate value theorem says that for function f continuous on the closed interval from a to b, there exists a number c between a and b, such that f of c equals n, which is any number between f of a and f of b. Now here are some English translations of what I just said. The diagram shows a continuous graph extending from x equals a to x equals b. Along the y-axis, f of a and f of b are marked, and some number n between f of a and f of b is shown. The intermediate value theorem basically says that a graph that is continuous from a to b will hit every function value from f of a to f of b on that interval. Your graphing calculator uses the intermediate value theorem to find zeros. Suppose we have a graph that is continuous from a to b, and f of a is positive and f of b is negative. Then by the intermediate value theorem, there must be a 0 somewhere in that interval because 0 is a number between f of a and f of b. If you've ever tried to use the second trace 0 command on your calculator to find the zeros of a graph, like y equals the absolute value of x or y equals x squared, you probably saw the error message, no sign change. In this case, the calculator is unable to find the 0 because it's expecting and not receiving a positive y value on one side and a negative y value on the other. Here's an example of an application of the intermediate value theorem. Suppose function f is continuous on the closed interval from 1 to 4 and has the function values shown in the table. The equation f of x equals 1 must have at least two solutions in the interval from 1 to 4 if a equals which of these numbers? we need to select a value of a that guarantees that the function will hit y equals 1 twice. Suppose we put the number 0 in place of a. Then by the intermediate value theorem, the graph will have to hit every number between y equals 4 and y equals 0 on the interval from x equals 2 to x equals 3. That's the first of the two solutions. Also, the graph will have to hit every number between y equals 0 and y equals 2 on the interval from x equals 3 to 4. That gives us the second solution, so the correct answer must be A, 0. This concludes our lesson on section 2.5, continuity.